Hi, my name is TASNEEM and I'm a student at UC Berkeley. This is my final presentation for the O-REU program at Texas A&M for my project, Regression Models for the Stacking Fault Energy of High Entropy Alloys. High entropy alloys, or HEAs, are a high-strength, ductile, and corrosion-resistant class of materials. Unlike traditional alloys which have one or two principal components, HEAs have 5 or more elements in near equiatomic proportions. This unlocks a vast, nearly infinite parameter space with the potential for tunable properties. You can choose how many elements to include, which ones, and in what proportions. Across the bottom, there are some models of what HEAs look like at the atomic level with an increasing number of components. For this project, I have focused on alloys with these 7 elements listed on the slide: iron, chromium, manganese, nickel, cobalt, vanadium, and aluminum. To navigate this parameter space, I focused on the stacking fault energy associated with different compositions. SFE is the energy per unit area associated with a stacking fault. As we can see on the left in the figure, a perfect crystal has an ABC, ABC, ABC pattern. On the right, we see an interruption of the pattern, ABA, and this interruption is a stacking fault. The scope of this project focused only on FCC compositions, and for these compositions, the SFE corresponds to stacking faults along the 1-1-1 direction of the crystal structure. SFE is important because it's indicative of how a material deforms, and this in turn determines macroscopic properties. Not much work has been done specifically designing HEAs based on this property. One challenge is that it's computationally costly to calculate SFE using the traditional DFT-based methods. That's where this project comes in. The immediate goal of this project is to use machine learning to quickly predict SFE. Ideally, the algorithms used are interpretable, so some insight is gained into the system. I have looked into developing models based on composition, but the real end goal is to develop a model based on elemental properties so that the model can hold true for a greater variety of systems. Long-term, such a model will improve the efficiency of HEA design by increasing experimental efficiency through the prediction of mechanical properties beforehand. Additionally, computational costs are reduced. 2 feature sets are being used to develop models. The first is composition. This refers to the proportion of elements in the alloys. They are what's used to calculate SFE directly from first principles, and they define which values we can access in terms of parameter space, that is, which alloys form FCC structures. Furthermore, the composition data is visualizable with only 7 different inputs. The second feature set is the elemental property-based data. I found values of 17 different properties for each of the constituent elements. Then I took each composition data point and found what the corresponding weighted average and weighted variance would be for each of the properties based on this composition. To be clear, this dataset looks like 34 different inputs along with that same output of SFE. The purpose of training a model on this dataset is generalizability. If SFE can be predicted based on these properties, the model developed would be element agnostic, lending itself to a much larger range of compositions. These are the different elemental properties that we chose to look at. Some are more physical properties like melting point and shear modulus, and some are more related to electronic properties like electronegativity. 2 that stand out are these lattice stabilities. This is the energy difference between hexagonal close packing and FCC packing for an element. The lattice stabilities were derived using 2 different approaches. The first one is DFT-based, using ab initio calculations that only use atomic number and atom positions as input. The second is thermodynamics-based. Both were included since both are valid modeling strategies. Lattice stability was found to correlate strongly with SFE, most likely due to its involvement with stacking patterns. I started this summer with visualizing the composition dataset. One tool I used was T-distributed stochastic neighbor embedding, or t-SNE for short. t-SNE defines a probability distribution based on distances between points in the original higher dimension, and then finds a similar distribution in the lower dimension. Then, points are mapped to the lower dimension so that they can be visualized. In this case, we can visualize our 7-dimensional parameter space in 2D. Here's what our t-SNE plots look like. On the left, I have the background by itself. This consists of a collection of points, not necessarily part of the SFE dataset, but simply points used to construct the background. Compositions with the majority element are plotted with the color corresponding to the label. For example, the compositions with the majority of nickel are plotted in cyan. On the right, there are 3 layers involved. On top of the background layer, there's a layer of black points, and these represent compositions that form FCC alloys. This defines which points our model applies to. On top of that, the dataset is plotted with the color corresponding to SFE, green being greater values, and red being smaller, more negative values. One obvious trend we see is the decrease of SFE going from nickel to cobalt. This can be explained by the nickel-cobalt binary. Nickel tends to form FCC structures and cobalt tends to form HCP structures. A stacking fault in a cobalt majority alloy would be much more energetically favorable, since the cobalt favors a stacking pattern that a stacking fault would create. At the start of the summer, I had 426 points, plotted in the left figure. These points met additional specifications beyond simply being FCC structures, and this narrowed the compositions down considerably. The black layer still represents compositions that can form FCC structures. As you can see, a lot of the space is not represented, particularly high manganese compositions and compositions closer to the middle of the plot. We wanted a robust model, so over the course of the summer, we added 100 more points, shown in the right figure. Note how the points on the right are more spread out than those on the left. The t-SNE plots show that our data is imbalanced. It's not uniformly sampled from the design space. When training a model, we run the risk of the scenario on the left. Here, the model shown in brown overfits to a cluster of training points shown in blue, neglecting the undersampled white points in the top right corner. To address this, we used k-metoid clustering to resample the data so that the training set was more uniformly distributed throughout the design space. In principle, this would be the scenario on the right, where the model better fits all of the data because the resampled points are more evenly distributed. These are the models outlined in the scope of this project. I've investigated Gaussian process regression and support vector regression so far. Future plans include testing decision trees, which excel at modeling the discontinuous jumps typical of phase diagrams. Next is CISO. CISO stands for Sure Independent Screening and Sparsifying Operator. In principle, it carries out nonlinear regression while simultaneously narrowing down the number of features used in the model. This is of interest particularly for the property feature set because the chosen features might lend us some insight into the nature of HEAs and SFE in general. These are the results from investigating resampling for GPR and SVR. For each K value, 10 models were trained on a dataset of that number of metoids, and the cross-validation accuracies were averaged. We can see here that the GPR accuracy drops off with increasing K, most likely due to overfitting. Additionally, we see that the SVR achieves higher R-squared values overall, hanging around 0.9, whereas the GPR peaks around 0.7. Plots like these can tell us about model performance, qualitative information of how the data is distributed, and the intersection of these two factors. The best performing model with the highest R-squared value so far for the property-based feature set takes 260K metoids and then fits a support vector regressor. On the right, I have plotted the 10-fold cross-validation PVA plot. Each of the color represents one of the folds. PVA plots plot model predictions against the true values. This can be used to check for under or overestimation, as well as how the accuracy changes over the output values. For example, it appears that this model has more trouble predicting SFE for lower values. To continue this project, the algorithms and resampling techniques for an elemental property-based model of SFE will be optimized. The next phase after that will be testing how generalizable the model is and working to make it even more generalizable by predicting SFE for new compositions and then using these in trials in turn to further refine the model. To conclude, I want to give a huge thank you to the O-REU program at Texas A&M and the NSF for funding this project. Thank you so much to my mentors Tanner Kirk and Guillermo Tovar Vasquez. Thank you to Prashant Singh for running our SFE calculations, and lastly, an enormous thank you to Dr. O-REU for guiding this project. Thank you.